Talk about the gradient descent algorithm. Okay, so gradient descent is an iterative first order optimization algorithm. So there is also an optimization algorithm which numerically finds where a function outputs its lowest value. That means a minima of a function, a local minima of a function. So what is a gradient? Gradient is nothing but a slope, or you call first order derivative or differential. You can represent a dy dx or f prime x. So there are different ways of saying a gradient. So here when we say gradient descent, that means we are trying to find out in which direction the gradient is decreasing, okay, for a function. So what is gradient? It's like for a certain value of change in y, what is the value of change in x? Now what is that change? So that is basically gradient descent is what function is trying to reduce, or find the slope of that function which is reducing. So gradient descent is used to minimize the cost function or the loss function, you can also say, for in the direction of the negative gradient. So that where it is going down, it's like a going downhill, and you know that the slope is decreasing, or you are trying to go downwards and try to find out the best way for yourself. So let's remind ourselves about the linear regression problem, where we are, it's a two variables, area and price, let's say x and y. So it's a two-dimensional plane because there are two variables, the three variables, three-dimensional, and more. Okay. So here we see, if we remember, we want to try to find a line which will fit the predictions, and then we try to see from the predicted value and the actual value, what's the gap, what's the difference. Okay, so that difference is called the residual. Okay, and then we find the sum of the squared errors, which is like the kind of average of the sum of the gradients. Okay, 1 over n, if there are n number of points, I equal to 1 to n, del I square, del I is the residual. Okay, so if this is the predicted point, sorry, this is the actual point, and this on the line is the predicted point, so del 1 is the difference, in the del 2, del 3, and because they can be above and below the line, so sometimes they can be positive, sometimes they can be negative, so we do the square, and then the difference will be normalized. So you see this one thing, that this is a quadratic function. Okay, so now if we try to plot that SSE, the sum of the squared errors, with respect to the intercept, so we get a parabolic graph. Okay, a parabolic curve. So one thing I will tell you, because of the quadratic function, this parabola is coming. But the important thing is that if you remember in the linear regression, what we do, that it's an equation of a line. Okay, there might be multiple parameters, but it's basically y equal to mx plus c, where the slope and the intercept, those we adjusted to fit the line best, so that the sum of the squared error was minimum. So now you see, when we say sum of the squared error is minimum, we are trying to come down in this function, that okay, intercept we change in such a way that the sum of the square error reduces until it finds the minimum point. So this is basically at every point, if we take this the tangent, and this is the kind of measure of the slope, and we find at this point this becomes the for it's a straight line horizontal to the x-axis. So so the for certain change of x, the y value doesn't change. Okay, dy dx will be equal to 0. So there are two ways of finding the minimum value of a function. So the first way is to find the minima, is to set the del f equal to 0. That means the first order derivative equal to 0. So it shows that for a change in x, the change in y is 0. That means the function is constant, or the slope does not change. So you have to understand that the slope reduces or decreases or descends up until this point, but after this point again slope will increase for the increase in the intercept. Okay, for the increase in x. So at that particular point, del f del y del x equal to 0, and we take an example and try to show that we can easily calculate using that when x equal to 2. But if this function is a very complicated and a large function with many dimensions and many other parameters, then a simple dy dx will not be possible to solve. So then we try to solve it numerically by manipulating all the parameters, okay, numerically. So let's say this is a function fx equal to a0 plus a1x plus a2x squared plus until a4x to the power 4, or even bigger. So how we find the best value for a0, a1, a2, a3, a4 to minimize f of x by manipulating them numerically by changing the different constants and seeing that how. So we have to always remember that in the direction of descent of the gradient we will go, and then it's like a going downhill until we come down to the valley. Okay, so how we do that we'll explain about it, but here one thing I want to show you that this is still a univariate function. Okay, it's just a one variable x, but if there are multiple variables, these functions can be very complicated to solve. So simple derivative may not work, so you have to think about a partial derivative, and we'll talk about it in more detail.